Welcome students, we are back with another lesson. The Bose atomic postulates. So your first Bose atomic postulate is nuclear concept. An atom consists of a small and a massive central core called nucleus around which planetary electrons revolve. The centripetal force required for the rotation is provided by the electrostatic attraction between the electrons and the nucleus. So according to this postulates, let us consider this dotted line as your atom. Fine. This atom has a massive central core. This is the massive central core. Around this central core, the electrons, this black dot, can you see? This black dots revolve around this central core. So this massive central core is known as your nucleus. Fine. And in order for the electron to revolve around this one, it requires centripetal force, and that centripetal force comes due to the electrostatic attraction between this electron and this proton. Since electron is negative charge and proton is a positive charge, so there is an electrostatic attraction which gives rise to a centripetal force. Therefore my electron revolves around this circular orbit. Fine. Your next postulate is quantum condition. Of all the possible circular orbits allowed by the classical theory, the electrons are permitted to circulate only in those orbits in which the angular momentum of electron is an integral multiple of h by 2 pi. Here h is the Planck's constant. Fine. So before we discuss about this quantum condition, let us okay, what is the motion acquired by this body? Okay, let us say this is your stone. This stone has your mass m. Now if you throw this stone, what happens? It acquires some motion. So the motion acquired due to its mass is known as your momentum. And how do you write momentum? M times v. So this is your linear momentum. Okay. For example, you can consider it like this. Suppose you have a small stone and you have a big stone. Fine. Now, if this small stone falls on your head, will there be any difference? No. You won't feel any effect from this small stone. Whereas if this big stone falls on your head, what happens? You will feel some change. And why is it so? Because of its mass. So from where this mass is coming in, from where is this force coming into picture? This force is coming into picture due to its motion v, velocity v, and the mass small m. Fine. So the motion acquired by any body of mass m moving with a velocity, this is known as your momentum. And how you write down momentum? You denote your momentum as p, and this is in turn equals to the product of your mass times velocity. Fine. After we have got the concept of your momentum, now let us understand what is your angular momentum. Fine. Now suppose this is your body. If this body revolves in a circular motion, fine. Now why is it able to maintain its circular motion? It is due to its angular momentum. Fine. If we are considering momentum in a circular motion, we'll call it as your angular momentum. Fine. So this is your angular momentum. And what will be the direction of the angular momentum? The momentum will be in the upward direction. Okay. to find out the direction of this angular momentum, you can use this concept. Okay, you take your hand, fine, you take your hand and curl around its motion. Let us say this is moving from right to left. Okay, if this is moving from right to left, you curl your hand around this motion, and the thumb will point the direction of the angular momentum. Fine. So the motion acquired by a particle moving in a circular motion is known as your angular momentum. This angular momentum in turn is denoted by L. Fine. Now your angular momentum is the product of the mass of the body, this body, times the velocity with how much speed it is moving, times the radius, or I'll say the distance of the position from the center of the motion. Fine. So this is known as your angular momentum. Only those circular orbit, like in this case this dotted line, only this kind of circular line will be allowed, or this kind of circular orbit will be allowed, for which the angular momentum of this circular orbit is an integral multiple of h by 2 pi. So h is your Planck's constant. So mathematically I can write your angular momentum L equals to m times v times r equals to integral multiple. Integral I can represent it with small n. N can be your any integer. That's why it is an integral multiple of h by 2 pi. Fine. Here L, m, v are the angular momentum, mass, and the speed of the electron. R is the radius of the permitted orbit. Fine. If this one satisfy this condition, then this orbit will be allowed. So this is your permitted orbit, and the radius, this radius will be the radius of the permitted orbit. Fine. Here in this case, the n is known as your principal quantum number. This above equation, L equals to mvr equals to nh by 2 pi, is known as your Bose famous quantum condition. Fine. Fine. Stationary orbits. While revolving in the permissible orbits, an electron does not radiate energy. These non-radiating orbits are called stationary orbits. So if an electron, let us say consider this electron, let us say it is revolving in our ground state, okay, the lowermost orbit. So if this is a allowed orbit, or I'll say if this is your permissible orbit, then in this case the electron which revolves around this orbit will not give any energy. Fine. So such kind of orbits will be known as your stationary orbits. Fine. Next, Bohr postulate frequency condition. An atom can emit or absorb radiation in the form of discrete energy photons only when energy jumps from a higher to a lower orbit, or from a lower orbit to a higher orbit respectively. Fine. So let us consider an electron. Okay, suppose this is your electron. Okay, if this electron wants to make a transition from excited level to ground level, what it has to do, consider your first case, if it has to make a transition, it has to give away the extra energy. We know E2 is at higher level, so your excited level has more energy. In order to go to a lower level, it has to give away its extra energy. Fine. The other way around is also possible. Suppose this is your electron. The electron is in the ground state. Now, in order to make a transition to a higher excited state, or let us say to a higher energy state, what happens? It has to get some energy. Therefore, it absorbs some energy, h nu. Fine. And in the previous chapter, we have already studied these energies are in the form of a wave packet, or they are also known as your photon. Fine. Your energy. So an atom can emit or absorb a radiation in the form of discrete energy photons only when the electron jumps from a higher to a lower orbit or lower to a higher orbit respectively. Fine. Now if E1 and E2 are the energies associated with the permanent orbits, then the frequency of the emitted absorbed radiation is given by, okay, if E2 is the energy level of this excited level, E1 is the energy of this ground level, then the difference of the energy is denoted by delta E. Fine. And this delta E equals to how much amount of energy? It is equals to h nu. So I can write E2 minus E1 equals to delta E, which in turns equals to h nu. So I've written here h nu equals to E2 minus E1. So this is your famous Bose frequency condition. From here you can find out the frequency using this relation. Fine. Bose theory of hydrogen atom. Fine. Let us consider this as your hydrogen atom. This hydrogen atom has a nucleus around which an electron is revolving in a circular orbit. Fine. Your electron has a negative charge, whereas your nucleus has plus Z. In this case, what is your plus Z? Your Z denotes how many protons are there inside the nucleus. Fine. And E denotes the charge of the proton. Now, for a hydrogen atom, Z equals to 1 means inside the hydrogen atom's nucleus there is only one proton. So in our case, Z should be 1. Fine. So if I have to consider the total charge, what will be the total charge? It will be number of protons times the charge of a proton, which is plus Ze. Fine. And if I have to write down the Coulombic force of attraction, how will I write? The force between this electron and proton can be written as F equals to K Ze, charge of the proton, Ze, times the charge of the electron, E. The charge of the electron is minus E times the distance between the two charge, which is R square. Fine. Okay. So in which direction your force will be, or in which direction, or what will be the direction of your force? It will be towards the positive charge. Now for our simplicity, or rather say for our derivation, we will consider the charge in the other direction, in the opposite direction. So in order to consider the charge in the opposite direction, what do I have to do? I have to introduce a negative sign here. Fine. So negative and negative becomes positive. So I can write my Coulombic force as F equals to K Ze square by R. And this force is directed from the center to the electron. Fine. Okay. So this is my Coulombic force. Now, as we know, whenever a body moves in a circular motion, it will gain a centripetal force. Fine. This centripetal force is directed towards the center. So what will be the centripetal force for this electron? It will be mass times the velocity with which this electron is revolving, the square of the velocity. Okay, mass times the square of the velocity in which direction it is moving, divided by the distance towards the center. So my centripetal force I can write as mv square by r. Fine. And we know our Coulombic force, it was directed from the proton to the electron. And our centripetal force is directed from electron to the proton. Now in order for this electron to revolve in this circular orbit, what it has to do? It has to balance these two forces. My centripetal force should be equal to your Coulombic force in order for the electron to revolve in a circular orbit. If any of one of this force is greater, what happens? If your centripetal force is greater, the electron will fall towards the center. If your Coulombic force is greater, what happens? The electron will move away from the center. So in order for this electron to revolve in a circular orbit, your centripetal force should be. Now I can, on simplification, I can say cancel this r square from here. So I can write mv square equals to kze square by r. Now I can send this r here, send this mv square to the denominator. I can write r equals to. So we remember from Bohr's quantization condition that our angular momentum L, which equals to mvr, should be equal to the integral multiple of h by 2 pi. From here also I can find out my value of r. I can send this mv to the other side. Therefore I can write my radius as nh by twice pi mv. Fine. Now equation 2 denotes the equation for radius, whereas your equation 3 also denotes your equation for radius. I can equate this to equations. Fine. Therefore, on equating our equation 2 and equation 3, I can write kze square by mv square equals to nh by 2 pi mv. Fine. Now here I can cancel this square. I can cancel this mass. So I'm left with only velocity. Fine. So in order to find the expression for this velocity, what I'll do? I'll send this velocity to the numerator. I'll send this quantity nh to the denominator. I'll send this quantity 2 pi to the numerator. My velocity as twice pi k ze square by nh. Okay. So we'll substitute this value of the velocity in our equation 3. In equation 3, it was nh twice pi mv. Fine. Substitute this value of v. I can write nh twice pi m 2 pi k ze square by nh. nh and nh I can write n square h square. 2 pi times 2 pi will give me 4 pi square. I'll write m k z e square. So this is the radius of the stationary orbit. Fine. So how will I do? I will substitute this value of n as 1. So 1 square will be 1. So what will be the radius of the first orbit or your ground level? R equals to h square 4 pi square mk ze square. If I want to say I want to find out the radius of the first orbit of hydrogen atom, then what I have to do? I have to substitute this value of z as 1. So I'll write r equals to h square 4 pi square mk e square. Fine. Now if I'll say I have to find out the radius of the second or my first excited level, what I'll do? I'll substitute as 2. 2 square will give us how much? 4. This 4 and this 4 gets cancelled. My radius will be h square m square pi square mk e square. So basically this expression give us of the stationary orbit. Fine. The radius of the hydrogen atom, called as Bose radius, can be determined by putting the value of z equals to 1 and n equals to 1 in equation 5 Therefore, we denote it by R naught. Fine. So R naught equals to, put n equals to 1, and in the denominator put z equals to 1. Now substitute this value. H is your Planck's constant, which is 6.63 times 10 to the power minus 34 joule second. Write down 4 pi square. Fine. Your mass of the electron, how much is the mass of the electron? 9.11 times 10 to the power minus 31 kg. What is K? K is your force constant, which is 9 times 10 to the power 9. E is your charge of the electron. Write down 1.6 times 10 to the power minus 19 whole square. Substitute these values, do the calculation. So after completing the calculation, I got the radius of the innermost orbit, or I say Bohr's radius, to be around 5.29 times 10 to the power minus 11 meter, or I can also write it as 0.53 angstrom. This angstrom means times 10 to the minus 10 meter. Fine. Instead of writing 10 to the power minus 10 meter, I will simply write angstrom. So I have 0.53 angstrom. So if this is your hydrogen nucleus, this is your first stationary orbit or your innermost orbit. So what will be the radius of this innermost orbit? It will be 0.53 angstrom. Fine. After we have calculated the radius of the hydrogen atom or your Bose atomic radius, now let's find out the speed of the electron in our hydrogen atom. Now using our equation 4, I can write P equals to 2 pi k Z e square nh. Again for hydrogen atom, what is this Z? The number of protons, Z equals to 1. Substitute Z equals to 1, I can write 2 pi k e square nh. Okay. Now what I can do is I can multiply C on the numerator and denominator. Fine. There's no problem in this one. Okay. So I can write 2 pi k e square ch C by. Fine. Now look here. 2 is a constant, pi is a constant, force constant, k is also a constant, charge of electron is also a constant, c speed of light is also a constant, h Planck's constant is also a constant. Let's write all of these constants in a bracket. Outside the bracket, I'll write c by n. C is the speed of light, n is the nth quantum state, or I'll say my principal quantum number. Now, after writing all of this constant, I know if I simplify these values, I will get a certain value which will be a constant, which will not change for any medium or anything. Fine. So let us replace this with another constant alpha. This alpha is known as your fine structure constant, which is equals to 2 pi k square ch. Fine. So my velocity of the electron, I can write it as alpha c by n. Fine. So what will be the velocity of the electron in the hydrogen atom? It will be what will be the, it will be v equals to alpha c by n. C is the speed of the light, n is the principal quantum number of that state. If this is your nucleus, this is your first excited state, what is the value of n in this case? N equals to 1. If n equals to 1, what will be the velocity of this electron? This will be c alpha. C is the speed of light, alpha is the energy of the electron. Fine. Now, as our electron is revolving around our circular orbit, okay, this is my nucleus, this is my circular orbit. As my electron is revolving around your circular orbit, okay, since it is moving in a stationary orbit, or let us say like this. Okay, this is my first excited state, this is my second excited state, and so on. Okay, let this be my nth excited state. Okay, in between, I don't know, there can be n number of excited state.
So let us say the energy state for this one is En. The energy state, this is my second energy state E2. This is my first energy state E1. Fine. Now let us consider an electron which is revolving in this nth state. Okay. Now as the electron is in motion, okay, we know whenever a body is in motion, it has a kinetic energy associated to it. Now kinetic energy can be written as half mv square. Okay. And we know, or we have derived from our equation 1, this half mv square equals to kz e square by twice of r. Okay. This, from where we have derived this one? We have derived this one from our equation. Remember this mv square by r. What is this one? This was my angular momentum. The angular momentum should be equal to what? It should have been equal to the Coulombic force of attraction. Right. Now I need half mv square. What I can do? I can cancel this r from both the sides. Okay. Apart from this one, I need half. So let us multiply half on both sides. So mv square by 2 equals to k z e square by twice of r. Right. So what is this one? This is my kinetic energy half mv square, which in turn equals to kz e square by twice of r. Right. Okay. Now, as the electron is in your nth energy state, it must possess some potential energy, isn't it? So what will be the potential energy? The potential energy of a charge in a electric field. What is the potential energy of a charge in an electric field? We have studied from our electrostatics chapter. It is equals to k times q1 q2 by r. Okay, what is q1? Q1 is the charge of the proton. Okay, charge of the nucleus. How much is the charge of the nucleus? Plus Ze. So q1 equals to Ze. Fine. What is q2? Q2 is the charge of the electron, which is minus E. Fine. Divided by r. On simplification, I can write minus kze square by r. Fine. Now, this electron has kinetic energy. This electron has potential energy. So what will be the total energy of the electron? The total energy of the electron will be the sum of kinetic energy plus potential energy. I can write kze square by twice of r, which in turn equals to minus, or I can write what is my kinetic energy? Kze square by twice of r. Potential energy is minus kze square by r. On simplification, I'll get kze square by twice of r, negative sign. Right. Now we have derived the value of r, isn't it? R was n square h square 4 pi square mk ze square. Substitute the value of r. Fine. Simplify this. We get the energy of the nth orbit, which in turn equals to minus 2 pi square mk square z square e to the power 4 n square h square. Fine. Now this is my energy state, isn't it? Energy state of the nth orbit. And do you notice this negative symbol here? What does this negative symbol denotes? The negative symbol of the total energy denotes that the electron is bound to the nucleus. That means it has some electrostatic energy, isn't it? So if you want to remove this electron from the nucleus, what you have to do? You have to supply this extra energy, which is minus 2 pi square mk square z square e to the power 4 n square h square. So this denotes your energy of the electron in this nth orbital state. Fine. If you want to find out this energy in your first orbital state, what you have to do? Substitute the value of n as how much? N equals to 1. Substitute the other one, they are just your constants. Only 2 is a constant, pi is 3.14, m is mass of the electron, 9.1 into 10 to the power minus 31, k is your force constant, 9 times 10 to the power minus 9, z is the number of protons, how many protons hydrogen atom has, z equals to 1, e is the charge of the electron, 1.6 into 10 to the power minus 19, n we are calculating for your first energy excited state. Substitute the value of n will be how much? 1. Then h is how much? H is your Planck's constant. What is your Planck's constant value? It was 6.67 times 10 to the power minus 27 or something. 6.6. Okay, so let us substitute for hydrogen atom, z equals to 1. Substitute these values, how much we get? Twice of pi square mk square e to the power 4 by h square. Okay, fine. Now let us calculate the energy of the first orbited state. We have n equals to how much? 1. Substitute n equals to 1. Fine. Now substitute these values to pi value is how much? 3.14. M value is how much? 9.11 times 10 to the power minus 31. What is the value of k? 9 times 10 to the power 9. What is the value of E? 1.6 times 10 to the power minus 19. What is H? H is 6.63 into 10 to the power minus 34 whole square. Fine. And what is N? N is 1. Now after you calculate, you will get something around 21.76 10 to the power minus 19. Converted into electron volts, you have minus 13.6 electron volts. Fine. So if this is your nucleus, this is your first energy state. So the electron which is revolving in the first energy state has an energy how much? Minus 13.6 electron volt. Now let us, like, suppose if you have any, so a certain set of experiment, okay, where it can supply energy. Okay, now if you supply an energy of how much? Minus 13.6 electron volt, what happens to this electron? This electron will jump from its energy state, isn't it? This electron will jump from its energy state, or it will be ejected from this orbital state. Okay, so it will go to a different energy state. Now before we study about this different energy states, let me introduce one concept which is known as your wave number. Okay, now suppose this is your nucleus, this is your first excited state, this is your second excited state, this is your third excited state. Okay, now let us say this is your electron. This electron goes from this energy state to this energy state, and when it is possible, when it absorbs certain energy, isn't it? Okay, or I can consider the opposite case also. If this is your energy, this is your electron, if it wants to go from a higher state to a lower state, it has to give certain energy, isn't it? So let us say this denotes your energy, the energy which it is giving, and we know energy is in nature of a wave. Okay, fine. So if it is going from higher to a lower, more energy as compared to this one, isn't it? It has to jump from first to 1 2 3, first to third state. That means it has to gain more energy, or I can also say when it has to jump from third to first state, it has to give more energy. More energy means more waves as compared to this one. When it is jumping from second to first state, that means it is giving less energy, then it has less waves. Okay, so here can you see the different waves which is being emitted or you absorb? Yes, so this wave we will take into consideration. Okay, now let me introduce a new concept which is your wave number. This wave number tells us, let us say, in a unit distance. Okay, Suppose this is my unit distance, 1 unit distance. How much wave does it travel? This is my wave number. Fine. In this case, this is my one wave. This is my zero point 0.5. In this case, it travels, if it has to travel from first to second or second to first, how many waves it has to travel? 1.5. But in this case, when it has to travel from your first to third state, or I'll say third to first state, how many waves it has to travel? One wave, two wave, three wave, 3.5. So by this way also I can get the idea about the energy state, isn't it? By this wave also I can get a picture of this energy state, or let us say in which orbit it is revolving. Okay, so it is in a different orbit, then it has different energy state, different energy state, different waves. So the next thing we have introduced, wave number, how much wave it is traveling per unit distance. And how to calculate this one? Suppose lambda is your wavelength, then my wave number can be written as 1 by lambda. Why 1 by lambda? Because how much waves it is traveling in a unit distance. Fine, so I'll divide it with 1. Okay, so this wave number is denoted by v bar, which in turn equals to r 1 by n1 square minus 1 by n2 square. Fine, this r is known as your Rydberg constant, and its value is somewhere around 1.09 times 10 to the power 7 meter inverse. Okay, n1. n1 denotes your first orbit, n2 denotes your second orbit. Fine. Or let us say n1 denotes your this ground state, or n2 denotes your final excited state, whether it's your second excited state or your third excited state. Okay, this n2 denotes your final excited state. It can be any one of this one. Let if it is jumping from 3 to 1, then yeah, instead of n2 this will be n3. Fine. And n1 is your moving on. So what the scientists have done, they have studied this different wave propagations or your different energy propagations. What they have noticed, let us say the first energy state, or your this n equals to 1 represents your first energy state, n equals to 2 represents your second energy state, n equals to 3 represents your third energy state, n equals to 4 represents your fourth energy state, n equals to 5 represents your fifth energy state, n equals to 6 represents your sixth energy state, and so on. Okay, so various scientists has performed their experiment and studied this. Okay, so one of the scientists, he studied this. He noticed that the electrons can jump from your sixth energy state to your first energy state. The electrons can also jump from your fifth energy state to your first energy state. The electrons can also jump from your, this is how much, third energy state to your first energy state. The electrons can also jump from your second energy, sorry, your third energy state to your first energy state, and this one, second energy state to your first energy state. Okay, so whenever the electron make this kind of transition from any state to your first state, okay, when electrons make this type of transition, they radiate some energy. This energy is in the ultraviolet region, or I'll say the energy being emitted is the ultraviolet waves. Okay, and this various jumps, or I'll say this various series, was named after Lyman, which is known as your Lyman series. Okay, so what happens in Lyman series? If an electron jumps from any higher energy state, okay, any higher energy state, let us say in this case my final or my higher energy state N2 can be your 2, can be your 3, can be your 4, and so on. Whenever your electron jumps from your any higher energy state to your first energy state, n equals to 1, n equals to 1, okay, then we get a spectral series. Okay, we get a spectral series, means if this is jumping, okay, so as you can see, when the electron makes transition from any higher energy state to your first energy state, it gives out energy. This energy falls into the region of ultraviolet region. So what the scientists have performed, they have performed this experiment, and in this experiment, can you see this particular spectrum or this particular spectrum of light? This is the series of light which is obtained when the electrons jumps from any higher energy state to your first energy state. In that case, the energy produced was around 400 nanometer. Okay, so this is your ultraviolet rays. Okay, so when this spectral series takes place, what happens? You get a ultraviolet rays, and this spectral series is known as your Lyman series. Fine. In the similar manner, when the electron makes transition from your higher state from another higher state to your second excited state to n equals to 2. Now in this case our value of n is 2, fine, and your higher energy state n2 can be your 3, can be your 3, can be your 4, can be your 5, can be your 6. Whenever such kind of transitions takes place, it gives rise to another set of region. This series or this spectrum is known as your Balmer series. Fine. Now, when an electron makes a transition from your higher excited state to your third energy state, okay, it gives your energy somewhere around this region. Okay, in this region, it gives infrared. Okay, the energy emitted is infrared wave. So what will be the formula for this case? The wave number will be R equals to 1 by 3 squared. 3 denotes your in which energy states they are jumping, your third energy state. This is your third energy state. Okay, from which higher excited state it can jump, from fourth state, it can jump from fifth state, it can jump from sixth state, and so on. Fine. Now whenever an electron makes such kind of transition, it emits the energy, or it gives. Now when an electron makes a transition from a higher energy state to your fourth energy state, okay, this one, okay, this is your fourth energy state. When an electron makes transition from a higher state to your fourth energy state, it gives out series of energy. Okay, this series is known as your P fund series. Sorry, this series is known as your bracket series. when an electron makes a transition from a higher energy state to your fourth energy state, this is known as your bracket series. In this case, N2 equals to 5, 6, 7, and so on. Now this also falls under your infrared region. Okay, this is your infrared region. Fine. Moving to our last one. When an electron makes a transition from any higher energy state to your fifth orbital, n equals to 5, then that kind of series will be known as your p1 series. Okay, in this case also the energy which is produced, it also falls under the infrared region. Fine. So let us revise what we have discussed so far. So when an electron makes a transition from higher energy state to your first orbit, it is known as your Lyman series. It gives out the energy in ultraviolet region. When an electron makes a transition from higher energy state to your second energy state, then it gives energy somewhere around ultraviolet region only. Okay, this is known as your Balmer series. When an electron makes a transition from higher energy state to your third energy state, then this series is known as your Paschen series, and it gives out the energy in which wavelength, in the infrared region. Similarly, when a electron makes a transition from your higher energy state to your fourth energy state, n equals to 4, then in that case also the energy emitted falls under your infrared region. Again, when the electron makes a transition from higher energy state to your fifth excited state, in that case also you get the energy which falls under your infrared region, and this is known as your p1 series. Okay, now let's draw the energy level diagram. Okay, before we draw the energy level diagram, let us calculate the energy level of hydrogen. Now we know the energy equation, En equals to minus twice pi square mk square z square e to the power 4 n square h square. Substitute the value of z equals to 1. In this case I can write minus 2 pi square mk square e to the power 4 h square, divide by 1 by n square. Fine. Now the energy of the electron in the first orbit. Okay, for the first orbit, what will be the value of n? N equals to 1. Substitute this value here. Do this calculation, you will get minus 21.76 10 to the power minus 19. Convert this one into your electron volts. I have minus 13.6 electron volts. So what is, if this is my nucleus, this is my first excited or my first energy state, or let us say this is my ground state, then what will be the energy of this ground state? Minus 13.6 electron. Okay, now look here very carefully. Up till here you have calculated this value. Okay, n square equals to 1, so you have taken this out of your calculation, so you have calculated up till this value. Okay, now if I'll say you have to calculate the energy of this excited state or your first excited state. Okay, in this case you will again use this equation. In this equation all the parameters are same except for this n square, is it? And we have calculated the value of this parameters, and how much it comes around? It comes around minus 13.6 electron volts. So instead of writing, or instead of doing the calculation again and again, I can simply write, instead of this one I can write this one as the energy state of the first energy level, that is your ground level E1, and E1 is how much? Minus 13.6 divided by n square. So if I want to find out the energy state of my second orbit, what I have to do? Minus 13.6 divided by 2 square. If I have to find out my energy for the third state, minus 13.6 divided by 3 square. Okay, so this is the energy equation, and this makes my calculation very simple as compared to this one, isn't it? and this will be also useful for solving numericals in your exam. So we will use this energy equation throughout. Okay, if you have any confusion, how did I got this one energy equation, you can ask me on the WhatsApp. I will re-explain it to you again. Right? As I've stated, my E1. E1 is how much? 13.6 electron volt. Okay, using our equation of energy En equals to minus 13.6 electron volt divided by n square. Let us calculate the energy for our second orbital state, which comes around minus 3.4 electron volt. Third energy state minus 1.51 electron volt. Fourth energy state minus 0.5 electron volt. Fifth energy state minus 0.54 electron volt. Sixth energy state minus 0.37 electron volt. Right? So in this manner, I can calculate the energy of any excited state. Right? So let us take our first energy state as our reference. Okay, minus 13.6. Let us take this energy state as my reference, or let us say this is my ground state. So this state represents my 13.6 energy level. Okay, minus 13.6. Where am I getting my second energy level? At the energy level of minus 3.4. So somewhere at the energy level of minus 3.4, I am getting my second energy level. This energy level denotes the energy level of which orbit? N equals to 2 orbit. Fine. Now moving on, where I'm getting my third energy level at 1.5. This one. At this energy level, what is the value of N? N equals to 3. Moving on. Fourth energy level. How much is my fourth energy level? Minus 0.85. This one. What is the principal quantum number for this one? N equals to 4. Okay, similar and so on. You can draw for the fifth energy level 0.54, for the sixth energy level 0.38, for the seventh energy level minus 0.28, and so on. Okay, now look here very carefully. Now we have studied our spectral series. When an electron makes a transition from a higher state to the first excited state, that means minus 3 point from my minus 3.4 to minus 13.6. Okay, or let us say from 1.5 minus 1.5 to minus 13.6, or let us say from minus 0.85 to minus 13.6, or let us say from minus 0.54 to my minus 13.6, or minus 0.38 to my minus 13.6, or minus 0.28 to minus 13.6, or I can say when it makes a transition from any higher energy state to my first for my n equals to 1 state. What kind of spectral series it results? It results into Lyman series. As you can see in the bottom, this is my Lyman series, and whenever electron undergoes this transition, it gives out radiation which falls under which region? Ultraviolet region. Fine. Moving on, when the electron makes a transition from any higher excited energy state, this is the energy of those respective energy state, to your second energy level, which is minus 3.4, which denote my second orbital state. In that case, it gives us your Balmer series. Now, whenever electron makes this transition, it gives out energy which falls under which region? Visible light. Okay, fine. Similarly, when it makes a transition from this, when it makes a transition from any excited energy state to my third excited state, that is my minus 1.5, there's some extra energy which is given out. This is the extra energy. This extra energy falls in the infrared region. Fine. And this series will be known as your Paschen series. When an electron makes a transition from any excited state to your fourth energy level, this series will be known as your bracket series, and the energy given out will fall under infrared region. When an electron makes a transition from any excited state to your fifth energy level, then this will be known as your. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask.